Hi everybody, I'm Mr. Hassan. Welcome to Flipped Classroom Lesson 6.3, Convert Units of Weight and Mass. Today we're going to be in our textbooks on page 227, and that's all we're going to be working on today, just our textbooks, so that's all you'll need. Again, this is Flipped Class Lesson 6.3, Convert Units of Weight and Mass. We're in our textbooks, page 227. Alright, I'm going to refocus the camera. I'll see you guys soon.
Come back to camels. Here's a fractal. You start with these circles in a circle, and then keep drawing the biggest circle that fits in the spaces between. This is called an Apollonian gasket, and you can choose a different starting set of circles and it still works nicely. It's well known in some circles because it has some very interesting properties involving the relative curvature of the circles, which is neat and all, but it also looks cool and suggests an awesome doodle game. Step 1. Draw any shape. Step 2. Draw the biggest circle you can within this shape. Step 3. Draw the biggest circle you can in the space left. Step 4. See Step 3. As long as there is space left over after the first circle, meaning don't start with the circle, this method turns any shape into a fractal. You can do this with triangles, you can do this with stars, and don't forget to embellish. You can do this with elephants or snakes or a profile of one of your friends. I choose Abraham Lincoln. Awesome.
Okay, so here we are on page 227, lesson 6.3. Let's read from the top of the page. Convert units of weight and mass. The weight of an object is a measure of how heavy it is. Common units of weight in the customary measurement system include ounces, pounds, and tons. If we look over here, we can see what the conversion rates are. 1 pound equals 16 ounces, and 1 ton equals 2,000 pounds. Unlock the problem. Slide the book up here a little bit. Unlock the problem. The largest pearl ever found weighed 226 ounces. What was the pearl's weight in pounds? So here we need to say, in the green box here, you can see it says, how are ounces and pounds related? Well, 1 pound is equal to 16 ounces. Will you expect the number of pounds to be greater than 226 or less than 226? Explain. I would expect that to be less than. And I would expect it to be less than because every 16 ounces is equal to 1 pound. Okay, so now we're going to convert 226 ounces to pounds. Choose a conversion factor. Think, I'm converting pounds from ounces. So 1 pound equals 16 ounces. So we're going to use the rate 1 pound over 16 ounces. We're going to multiply 226 ounces by the conversion factor. And the conversion factor is going to be that 1 pound over 16 ounces. So here they have it set up for us. And you can see they're solving this the same way we solved units of capacity and the same way we solved units of length. Here I'm going to take my 226 ounces, put it over 1, multiply by 1 pound over 16 ounces. My ounces cancel each other out. I can simplify here. 2 goes into both of these numbers. 2 goes into 16 8 times, and 2 goes into 226 113 times. So it's going to give me, now they've already turned this into a mixed number. I have to do that yet. So I'm going to have 113 over 8 after I do my multiplication. 113 times 1 is 113, and 1 times 8 is 8. And now I'm going to convert this into a mixed number. So I'm going to bring my numerator and put it into my division house here. 8 goes into 113. Well, 8 goes into 11 one time. 1 times 8 is 8. 11 minus 8 is 3. Bring down my 3 here. 8 goes into 33. 8 goes into 33 4 times. 4 times 8 is 32. 33 minus 32 is 1, and so that's 1/8. So my answer is going to be 14 1/8 of a pound. Now they have theirs in 16ths because there's 16 pounds in an ounce. So the 14 is going to stay the same here. And now I've got to convert 1/8 into 16ths. Well, 2 times 8 is 16, so I'm just going to multiply my 1 by 2, which gives me 14 and 2/16 pounds. So this is a simplified version, and this is what the answer would be if we hadn't simplified here, cross-simplified our multiplication. So 14 and 2/16 pounds equals 14 pounds and 2 ounces. So the largest pearl weighed 14 pounds and 2 ounces. All right, let's look at the second part down here of our problem. The largest emerald ever found, whoops, sorry about that, bang the camera. The largest emerald ever found weighed 38 pounds. What was its weight in ounces? So choose a conversion factor. Think, I'm converting ounces from pounds. 16 ounces equals 1 pound, so we're going to use the conversion rate, 16 ounces over 1 pound. We're going to multiply 38 pounds by the conversion factor. 38 pounds times 16 ounces over 1 pound equals, and here you can see, they've canceled out their pounds, and now I've got 38 times 16, that's going to give me 608 ounces. So the emerald weighed 608 ounces. How would we convert the emeralds, or number one down here under explain? Explain how you would convert the emerald's weight to tons. Well, we could take 38 pounds and multiply it by the conversion rate, pounds over tons. So here we go. Or tons over pounds, sorry. So let's take 38 pounds and we're going to multiply that. We want to get tons and we want to get rid of pounds. So there are 1,000 or 2,000, sorry, pounds in 1 ton. Pounds are going to cancel each other out. And this is going to give me 38 over 2,000. And if I were to simplify that, I'm going to come over here a little bit more and reduce it by a factor of 2. Well, 2 goes into 38 19 times. And 2 goes into 2,000 1,000 times. So it'll give me 19 over 1,000 tons. All right, I'm going to turn to the next page. I'll see you guys in a minute.
Okay, but what about other shapes besides circles? For example, equilateral triangles, say, filling this other triangle, which works because the filler triangles are the opposite orientation to the outside triangles, and orientation matters. This yields our friend Sierpinski's triangle, which, by the way, you can also make out of Abraham Lincoln. But triangles seem to work beautifully in this case. But that's a special case, and the problem with triangles is that they don't always fit snugly. For example, with this blobby shape, the biggest equilateral triangle has this lonely hanging corner. And sure, you don't have to let that stop you, and it's a fun doodle game, but I think it lacks some of the beauty of the circle game. Or what if you could change the orientation of the triangle to get the biggest possible one? What if you didn't have to keep it equilateral? Well, for polygonal shapes, the game runs out pretty quickly, so that's no good. But in curvy, complicated shapes, the process itself becomes difficult. How do you find the biggest triangle? It's not always obvious which triangle has more area, especially when your starting shape is not very well defined. This is an interesting sort of question because there is a correct answer, but if you're going to write a computer program that fills a given shape with another shape following even the simpler version of the rules, you might need to learn some computational geometry. And certainly we could move beyond triangles to squares or even elephants, but the circle is great because it's just so fantastically round. Oh, just a quick little side doodle challenge. A circle can be defined by 3 points, so draw 3 arbitrary points and then try and find the circle they belong to. So one of the things that intrigues me about the circle game is that whenever you have one of these sorts of corners, you know there's going to be an infinite number of circles heading down into it. Thing is, for every one of those infinite circles, you create a few more little corners that are going to need an infinite number of circles, and for every one of those, and so on. You just get an incredible number of circles breeding more circles, and you can see just how dense infinity can be, though the astounding thing is that this kind of infinity is still the smallest countable kind of infinity, and there are kinds of infinity that are just mind-bogglingly infiniter. But wait.
All right, so here we are on page 228. Let's look at the top. Metric units. The amount of matter in an object is called the mass. Metric units of mass are related to powers of 10. So again, we're going to look at conversions, and they're going to be super similar to our metric units of capacity and our metric units of length. And here again, we are going to use our handy dandy chart to make these conversions. Let's look at the example here. I'm going to slide this up a little bit so we can see the whole thing. Zoom in. Okay, example. Corrine caught a rainbow trout with a mass of 2,570 grams. What was the mass of the trout in centigrams? What was the mass in kilograms? So we're going to convert this two ways. The first way that we're going to convert this is by using a conversion factor and multiplying. So you can see the conversion factor that we're going to use is we want to go from centigrams to grams. So 100 centigrams equals 1 gram. And we're going to multiply 2,570 over 1 by 100 centigrams over 1 gram. Very similar to how we solved the conversions on the last page. If I multiply this 2,570 by 100, all I have to do really is add two zeros. So we're going to write 2570 and add two zeros and then put my comma in, and I get 257,000 centigrams. So the trout's mass was 257,000 centigrams. All right, so let's look at another way. Use powers of 10. Recall that metric units are related to each other by factors of 10. And here you can see that to get smaller, we would multiply by 10. And to get larger, we need to divide by 10. And divide by factors of 10. And another way to think about it is to use the butt cheek method, right? So each time we have to move to the left, we're going to move one butt cheek to the left. And if we want to move to the right, we want to move one butt cheek to the right. So let's see how this works. 2,570 grams to kilograms. So we want to go from grams to kilograms. So we're going to count. 1, 2, 3. So we're going to need to move our decimal point 3 places to the left. So here you go. We've got 2,570. We're going to move that decimal point 3 places to the left, and we end up with 2 5700 kilograms. So, no, we did the so. All right, let's look at number 2. I'm going to have to slide the book up here a little bit so you guys can see. Suppose hoots and floops are units of weight, and 2 hoots equals 4 floops. Which is heavier, a hoot or a floop? Oh boy. Well, if 2 hoots equal 4 floops, well then hoots would be heavier because it takes less of them to make 4 floops. So the answer is hoots weigh more because it takes 2 floops to equal 1 hoot. Right? So if 2 hoots equal 4 floops, then 2 floops would equal 1 hoot. I'm just really glad that there isn't an actual unit of measure called hoots or floops, because I would just have a class of laughing children. All right, I'm going to take a break here, and we'll look at page 229. See you guys in a minute.
Pretend you're me and you're in math class. Actually, never mind. I'm sick, so I'm staying home today, so please pretend you're Stanislav Ulam instead. What I'm about to tell you is a true story. So you're Stan Ulam and you're at a meeting, but there's this really boring presentation, so of course you're doodling. And because you're Ulam and not me, you really like numbers. I mean, super like them. So much that what you're doodling is numbers, just counting, starting with 1 and spiraling them around. I'm not too fluent in mathematical notation, so I find things like numbers to be distracting. But you're a number theorist, and if you love numbers, who am I to judge? Thing is, because you know numbers so intimately, you can see beyond the confusing squiggly lines you're drawing right into the heart of the numbers. And because you're a number theorist, and everyone knows number theorists are enamored of prime numbers, which is probably why they named them prime numbers, the primes you've doodled suddenly jump out at you like the exotic, indivisible beasts they are. So you start drawing a heart around each prime. I mean, it was actually boxes, but in my version of the story it's hearts because you're not afraid to express your true feelings about prime numbers. You can probably do this instantly, but it's going to take me a little longer. I'm all like, does 27 have factors besides 1 and itself? Oh yeah, it's 3 times 9, not prime. What about 29? Pretty sure it's prime. But as a number theorist, you'll be shocked to know it takes me a moment to figure these things out. But even though you've got your primes memorized up to at least 1,000, that doesn't change that primes in general are difficult to find. I mean, if I asked you to find me the highest even number, you'd be like, that's silly. Give me the even number you think is the highest, and I'll just add 2 to it. Bam! But guess what the highest prime number we know is? 2 to the power of 43,112,609 minus 1. Just to give you an idea of what a big deal prime numbers are, the guy who found this one won a $100,000 prize for it. I mean, we sent our largest known prime number into space because scientists think aliens will recognize it as something important, not just some arbitrary number, so they'll be able to figure out our alien space message. So if you ever think you don't care about prime numbers because they're not useful, remember that we use prime numbers to talk to aliens. I'm not even making this up. It makes sense because mathematics is probably one of the only things all life has in common. Anyway, the point is that you started doodling this because you were bored, but ended up discovering some neat patterns. See how the primes tend to line up on the diagonals? Why do they do that? Also, this sort of skeletal structure reminds me of bones, so let's call these diagonal runs of primes prime ribs. But how do you predict when a prime rib will end? I mean, maybe this next number is prime, but my head is too fuzzy for this right now, so you tell me. Anyway, congratulations. You've discovered the Ulam spiral. So that's a bit of mathematical doodling history for you. You can stop being Ulam now, or you could continue. Maybe you like being Ulam. That's fine. But
Okay, so here we are on page 229. Convert to the given unit. All right, so let's look. Number 1 says 9 pounds equals blank ounces. So we want to think of a conversion factor that has ounces over pounds because we want to be able to cancel out those pounds. Well, 16 ounces equals 1 pound. So we're going to take 9 pounds, put it over 1, and multiply that by 16 ounces over pounds. Then my pounds will cancel each other out. And I can just multiply 9 times 16 and I would get 144. So therefore 9 pounds equals 144 ounces. Let's look at number 2. Here we have 3.77 or 3 77/100 grams equals blank decagrams. So here's my handy dandy chart that I've made up. And I want to go from grams to decagrams. To get from grams to decagrams, I have to go one place to the left. So I'm going to rewrite 3.77 here, and I'm going to move my decimal point one place to the left, and that's going to give me 0 and 377 thousandths decagrams. All right, let's look at number 3. Number 3 says, Amanda's netbook weighs 56 ounces. How many pounds does it weigh? So I'm going to take my 56 ounces and I'm going to multiply that by pounds over ounces because I want my ounces to cancel each other out. Well, there are 16 ounces in 1 pound, so that's my conversion rate. My ounces are going to cancel each other out, and I'm going to end up with, well, let's see, is there anything I can reduce here? Well, I'm not sure if 16 goes into 56, but I know that 8 goes into 16, and 8 goes into 56, so 8 goes into 16 2 times, and 8 goes into 56 7 times. So I cross-simplified there. 7 times 1 is 7 over 2. And that's going to give me 3 1/2 pounds. All right, let's look at number 4. A honeybee can carry a 40 milligram load of nectar to the hive. How many grams of nectar can a honeybee carry? Well, I'm going to start with 40. And I need to go from milligrams to grams. So here's my chart. I need to go from milligrams to grams. So I'm going to go 1, 2, 3 places to the left. So here's 40. There's my decimal point. Remember, for a whole number, your decimal point is all the way on the right. And I'm going to go 3 places left. 1, 2, 3. So my answer is 0 and 40 thousandths grams. All right, let's slide the book up here a little bit and do some of the on your own problems at the bottom of the page. So I've got 4 pounds equals blank ounces for number 5. 4 pounds equals blank ounces. So let's see, can you see this here? Let me slide this book down so I have a little room to work up there at the top. Let's do it here. So I've got 4 pounds over 1, and we want to multiply by ounces over pounds so I can get my pounds to cancel each other out. Well, there's 16 ounces in 1 pound. So if I multiply those together, my pounds cancel each other out, and I've got 16 times 4, which equals 64 ounces. So 4 pounds equals 64 ounces. Number 6 here says 7.13 grams equals blank centigrams. So here's 7.13. I need to go from grams to centigrams. So here's my chart. I'm at grams. I need to get to centigrams. I'm going to go 1, 2 places to the right. So let's do that. Here's 7.13. I want to go 2 places to the right. 1, 2, and I'm left with 713 centigrams. Number 3. Number 3 says 3 tons equals blank pounds. So I'm going to take 3 tons and put that over 1 and multiply it by pounds, because that's what I want to end up with, over tons. Well, there are 2,000 pounds in 1 ton. So if I multiply these together, 3 times 2,000 equals 6,000. So 3 tons equals 6,000 pounds. Let's look at number 8. Number 8 says, the African Goliath frog can reach weights up to 7 pounds. How many ounces can the Goliath frog weigh? Well, here I need to go from 7 pounds to ounces. I want to get rid of my pounds, so I'm going to use ounces over pounds as my conversion rate. There are 16 ounces in 1 pound, so I'm just going to, my pounds cancel each other out, and now I've got 7 times 16, which equals 112 ounces. And that's my answer. Number 9 says, the mass of a standard hockey puck must be at least 156 grams. What is the minimum mass of 8 hockey pucks in kilograms? Ow! Yuck! 2-part problem! Ugh. All right, let's take a look at this. Let's get serious for a second. So I've got to go from grams to kilograms, and they want to know how much 8 of them weigh. So for me, I'm going to convert grams to kilograms first. So let's do that. I'm going to take 156 grams, and I'm going to convert that to kilograms. And we're going to figure out how much 1 puck weighs in kilograms. So the way that we do that is, let me get my chart here. We're going to go from grams to kilograms. So that's 1, 2, 3 places to the left. So I'm going to take my decimal point for 156, move it 3 places to the left, and I have 0.156 kilograms. I know that's maybe a little bit hard to see, but it says 0.156 kilograms. So 156 grams equals 156 thousandths kilograms. And now I've got to take that 156 thousandths kilograms and multiply it by 8 because I have 8 hockey pucks. And the answer is going to be, if you haven't put it into your calculator and figured it out yet, you're waiting for me to give you the answer. The answer is 1 and 248 thousandths kilograms. So 8 hockey pucks are going to weigh 1 and 248 thousandths kilograms. Okay, so let's take a look at number 10. Number 10 says 250 pounds is greater than, less than, or equal to 2,500 tons. All right, I rewrote the problem I rewrote the problem on a piece of scratch paper here because I ran out of room. I'm not going to have enough room to solve this problem in the textbook. So I rewrote the problem on a piece of scratch paper here. What we're going to have to do is we're going to have to convert one of these values so that we can compare the two. Now I always like to convert larger values to smaller values because I know it's going to be a multiplication problem and not a division problem. So let's take 0 and 2500th tons and let's convert that to pounds so that we can compare pounds to pounds. So I'm going to have pounds over tons here because I want my tons to cancel each other out. Well, there's 2,000 pounds in 1 ton, so I'm going to have 0.25 times 2,000, and that will equal 500. My tons cancel one another out, and it's going to equal 500 pounds. So that means 0.25 tons equals 500 pounds. Therefore, 0.25 tons is greater than, what am I doing? 250 pounds is less than 0 and 2500th tons. So I'm going to come over here and I'm going to write that in my textbook. 250 pounds is less than 0 and 2500th tons. All right, let's take a look at number 11. Number 11 says 65.3 hectograms is less than, greater than, or equal to 653.
Major, please call the office.
Is greater than, less than, or equal to 653 decagrams. So here I'm going to get out my chart. And again, I want to convert the larger unit of measure because it's going to be, I'm going to get to multiply, and I'm going to move my decimal point to the right. So let's find my chart here. And I need to go from hectograms to decagrams. So I'm going to go one place to the right. So here's my hectograms. I'm going to take my decimal and move it one place to the right, and now I have decagrams over here. I know I wrote that real small, but I just crossed out my hectograms and turned it to decagrams. So now I have 653 decagrams is equal to 653 decagrams. All right, last problem, number 12. I've got 5 tons is greater than...
Mr. Rizika, please call the office. Mr. Rizika, please call the office.
This is what happens at the end of the day. The buzzer goes off and teachers get paged and we get interrupted. Just kidding. But anyway, all right, number 12. 5 tons is greater than, less than, or equal to 5,000 pounds. So again, I like to take my larger unit of measure and convert it to my smaller unit of measure. So I've got some space in my book to work here, so I'm going to write my work in my book this time. So I've got 5 tons, and I want to convert that to pounds. So I'm going to have pounds over tons so that my tons cancel each other out. Well, there's 2,000 pounds in 1 ton. My tons cancel each other out. 5 times 2,000 gives me 10,000. 10,000 pounds. So 5 tons equals 10,000 pounds. Therefore, 5 tons is going to be greater than 5,000 pounds. All right, that wraps up this week's flipped class lesson. I hope you guys enjoyed it. I'll see you guys next week with lesson 6.4. Mr. Hassan signing out.
Mr.
Turn around, all the bad things that you found. Turn around and pick yourself up off the ground. Turn around, listen for that happy sound. Turn around.
But you could also be Blaise Pascal. Here's another number game you can do using Pascal's triangle. I don't know why I'm so into numbers today, but I have a cold, so if you'll just indulge my sick predilections, maybe I'll manage to infect you with my enthusiasm. Pascal's triangle is the one where you get the next row in the triangle by adding up 2 adjacent numbers. Constructing Pascal's triangle is in itself a sort of number game because it's not just about practicing adding, but trying to find patterns and relationships in the numbers so that you don't have to do all the adding. I don't know if this was discovered through doodling, but it was discovered independently in France, Italy, Persia, China, and probably other places too, so it's possible someone did. Right, so I don't actually care about the individual numbers right now. You're still Ulam, right? So, like you would do, you pick a property and highlight it. For example, whether it's even or odd. If you circle all the odd numbers, you'll get a form which might be starting to look familiar to you. And it makes sense that you'd get Sierpinski's triangle because an odd number plus an even number equals an odd number. Odd plus odd is even, and even plus even is even. So it's just like the crash and burn binary tree game. Best part about it is that knowing these properties, you can forget about the details of the numbers. You don't have to know that this number will be 9 to know that it's going to be odd. But instead of 2 colors, let's try 3. We'll color them depending on what the remainder is when you divide the number by 3 instead of 2. Here's a chart. So all the multiples of 3 I'm a color red. Remainder 1 will be black and 2 will be green. The structure is a little different from Sierpinski's triangle already, but I'm tired of figuring out remainders based on individual numbers, so let's figure out the rules. If you add up 2 multiples of 3, you always get another multiple of 3, which is a sort of fact you use every day in math class, but here it means red plus red is red. And when you add a multiple of 3 to something else, it doesn't change the remainder of that something else. So red plus green is green, and red plus black is black. Remainder 1 plus remainder 1 equals remainder 2. 2 plus 2 is 4, and the remainder of 4 divided by 3 is 1, and 1 plus 2 is 3, remainder 0. The bottom line is that you're making up some rules as to what colored dots combine to get what other colored dots, and then you're following those rules to their mathematical and artistic conclusion. The numbers themselves were never necessary to get this picture. Anyway, those are just a couple examples of number games that are out there, but you should also try making up your own. For example, I have no idea what you get if you highlight the prime numbers in Pascal's triangle. Maybe nothing interesting, who knows? Or what happens if instead of adding to get the next row, you start with a 2 and a sea of invisible ones and multiply to get the next row? No idea what happens there either, or if it's already a thing people do or what. Oh wait, powers of 2. I know another way to write this. Okay, that makes sense. And then there's also a thing called Floyd's triangle where you put the numbers like this. So maybe you can do something with that too. Man, it seems like everyone has a triangle these days. I'm gonna take a nap.